All right, welcome everybody. This is the last presentation of the last day. We're all getting tired, so I'll try to get through this as smoothly as possible. So I'm David Chassin. Until last week, I managed the Grid Integration Systems Mobility Group at SLAC National Accelerator Laboratory. This week, I started my new company. Technically, I still have to present this on behalf of the lab since this work was largely funded and conducted at the lab. For those of you who don't know, SLAC is Stanford University's national lab. So I had the pleasure of working there for 8 years and working with some really brilliant students. Whenever I was in a room there, I was the dumbest person in the room, and it was great. They're really amazingly talented people. So Arras Energy is the Linux Foundation's commercialized version of a DOE tool. And so I'm going to talk about some of the history of the tool itself and how it came to be one of the LF Energy projects. It's important to go over this history because there's a lot of sort of backstory that influences how we think about this tool and how we try to use this tool today. And so I'll talk about that history. I'll talk about a lot of the capabilities that were put into the tool when DOE developed it and got moved over to Arras Energy when LF Energy adopted it. There are several user interfaces because really what GridLAB-D is an engine. It's not the simulator per se in the way that you might think about, say, Power World or even a tool like PSLF or PSSE. It's more and less in some ways. It really depends how you think about it. And then I'll wrap this up with, really sort of the thing that I really want to talk about is the challenges that you run into trying to make a tool like this open source. And I have to say, this was developed from the beginning. 25 years ago, when we conceived of this tool, we intended it to be open source. That turned out to be a lot harder than just saying it. And so I'll talk about some of those things. So I just want to recognize first all the organizations that have contributed to Arras Energy itself and its predecessors. So of course, SLAC is where most of the most recent work was done. And of course, with Stanford University PhD students who worked on the project. The Department of Energy has been key all along. And then Post Road Foundation, NRECA, PNNL was where it was originally developed. Hitachi, Southern Cal Edison, NREL, all these organizations were very much involved in the development of these tools. The California Energy Commission funded the latest iteration of the research. And we've been very involved with Amazon and fielding it and testing it at different utilities. There were some very large-scale tests of this software at National Grid, which we had a lot of assistance from AWS in getting that working. So, all right, so let me just kind of jump in to sort of the current status and just give you a sense of where things are, and then I'll go back over how we got there. So Arras Energy is the commercialized version of what the California Energy Commission called high-pass GridLAB-D, which is a high-performance version of the DOE tool. So the DOE tool you can think of it as a research tool. It was designed to solve a lot of problems that DOE wanted to study, and there were no simulators around that could do this, the kind of work that they wanted to do. So as a research tool, it really wasn't intended to be high performance. It wasn't intended to be usable by a utility. It was there to allow DOE to perform these studies and uncover things about the future grid rather than things about the present grid. So if you think about a lot of the tools we have today, they're very good at modeling what we do today. But can they model what we would like to do 20 years from now? That's a bit trickier. And DOE understood this, and it was a real limitation of the tools that they had at the time. Sorry? So the California Energy Commission had identified a number of use cases that they were very interested in studying more carefully, and they wanted utilities to be able to study easily with this tool. So they wanted to be able to do host and capacity analysis. And think about this like around 2016 timeframe when they were putting together the the grant funding opportunity for this, they wanted to study extreme events. They wanted to study deep electrification, and they wanted to study alternative tariffs. And these were all things that were very difficult to do with the tools that were available at the time. So we teamed up with Hitachi, with Pacific Northwest National Labs, and a number of other organizations to put together a pretty large-scale proposal. It was a total of $10 million that was spent on 3 different projects, including high-pass GridLAB-D, a project called OpenFIDO, which is another Linux Foundation LF Energy project, and a project called GLOW, which is the user interface I'll talk about, which Hitachi developed. So just going back over the timeline, the technology demonstrator was originally developed at PNNL back in 2002. I was part of that project, and it became GridLAB-D in 2007 when the U.S. Department of Energy decided to fund it full-blown development, and they supported, for about 5 years, they supported the development of the tool as an open source tool. And it actually became open source in 2007 in the sense that it was put onto, I think at the time it was Subversion. I think that's where it first showed up, and eventually migrated to GitHub later. So at the time it was one of the first forays by the U.S. Department of Energy into open source for this type of tool. The U.S. Department of Energy actually didn't even have a licensing mechanism that would allow it. They had to come up with one to allow us to do that. And we released the first version in 2008, and it was used for a number of studies. You can go look at all the papers, and you can see, conservation voltage reduction studies, and the taxonomy feeder development that was done by the Grid Modernization Initiative, and so on. This GridLAB-D was core to all of these research efforts. So in 2018, when CEC funded the development of the high-performance version, the plan was to commercialize through an open source mechanism. 2018 is the same year LF Energy was created. So CEC anticipated that there would be some kind of structure around that would allow us to do what we've done. And it was LF Energy came into being the same year this project was started. So at the time they didn't know it, but this was going to be the vehicle for open source release of this particular class of tool. When it was adopted by LF Energy in 2022, Shuli Goodman, who we fondly remember, named it Arras Energy. It was her sort of response to Tapestry, for those of you who know the other tool. All right, so I want to talk a little bit about the concept of operation in this tool. So the key thing to remember here is that the simulator is actually trying to simulate systems of systems. So you have to recognize that each of the systems that you're working with has its own solver. So if you think about, you've got a building or a bunch of buildings connected to a grid. You have a solver for the grid that's solving power flow, but you also have solvers for the energy and control systems in the buildings. These two can't talk to each other. They don't even work on the same time scale. So the challenge, of course, is constructing a solver that can coordinate all these different solvers. This is how Helix works, for example. It does the same thing. So the idea is that you have different objects that update at different rates, and you have to update each of the solvers at the appropriate rate, and they might have to share information between those updates. So you have to iterate through this process where one object says how long it has before a state change, and you do this for each object, and then you advance to the next state change, and then you redo the whole process. You do this until every object is satisfied that it no longer has any state changes, or you've run out of time. And so there's a whole process of event triggering in the simulator that deals with initializing the simulation, setting up the time-stepping system itself, and then running through the data updates with different iterations, processing through all the different objects to ensure that you don't update past an object's event change. So this is what the simulator does, and it takes an enormous amount of compute power to do this. You can make it efficient. It takes a lot of tricks and some interesting techniques to to make this run very quickly. It works out most of the time. And interestingly, you might imagine it doesn't always converge, but it does. When it doesn't converge, it's because you did something really, really wrong, like you have non-causal behavior in your control system or something. If you do things like they happen in reality, it will converge, which is really interesting. Okay, so the current status of the project, it's in a sandbox status. We're trying to get it up to the, what is it, after sandbox, I forget now. Sorry about that. So we need to, there are a number of things that we need to do to satisfy the Technical Advisory Committee that it's ready to move on to the next stage. And these involve sort of community building and road mapping and trying to get the development process a little bit stabilized. It's only been a year since it was adopted by Arras Energy. There's a lot of work to do still to get to the next stage. But if you look at what it's capable of doing, it has a remarkable range of capabilities that we can use already, and some interesting experimental capabilities. So it can solve both transmission and distribution power flow problems. For those of you who've done this, you know these are not the same problem. And it can do transient dynamics, but it's sort of in an experimental state, and it does switching between the two. So it detects when it needs to do a transient solution. It then performs the DAE solution for the transient, and then when it's stable, it returns to the quasi-steady state and then iterates the steady state solutions. So it's a really interesting technique that is used to do that. It models buildings, and it does different kinds of building models. It can do data-driven models or physics-based models, or both simultaneously. You can mix them. It has access to the full tariff database that comes from NREL, the OpenEI database. And so that allows you to do costing and revenue studies. It's got a retail market model that basically follows the transactive energy concept. So for those of you who are familiar, this is essentially real-time pricing at the retail level where devices can actually bid into a local energy market in order to solve the feeder constraint problem, for example. It has optimization. Being a Stanford shop, CVX is obviously in there. We've got examples where of MPC solutions that are in the iterative process, so it solves the MPC at every time step. Because CVX is so efficient, this is actually relatively straightforward to do. We've got weather data for online for North America. Sorry about not having the rest of the world online, but I'm sure you can figure out how to do that. It's not that difficult. And then we have all the sample feeders that are used for studies, the IEEE, the DOE taxonomy feeders, and then a bunch of feeders from PG&E, which are really sort of the most interesting ones. Those are quite complex. The largest feeder we've modeled, I think, is the 8500 bus, three-phase unbalanced feeder that IEEE has. We have a lot of data ingest and data recording mechanisms, straight CSV files, databases. I think one of the most interesting capabilities is the geodata capability. This allows you to present a panel of data which has both locations and time for a particular variable in the system. And so you can present, for example, all of the solar data for an entire country, for example, as a time series, and the simulator will then use that and make sure that everything is, all the correct objects have the correct values by their proximity to the locations in the panel. And then we have a very, very robust Python integration, which is how we get, for example, PyPower solver in there, and pandas and SciPy and sklearn and all the tools I think you would expect to see in a Python integration. As I said, there's really two major types of solvers. There's a distribution solver, which does the three-phase unbalanced solution that you need for distribution systems in the US. Not sure you necessarily need that anywhere else, but in the US this is a big deal. It uses different methods, so you have the ability to choose which solver method you want to use, and there's a converter from SIME. A lot of utilities use SIME, and so we have the ability to import SIME models to use with that. And then for transmission systems, we have a converter from PSSE. We don't have one for PSLF, Ironic since we're on the West Coast, but and then that converter basically just converts to pi power, which is essentially the basis for Panda power. It's the same, under the hood, it's basically the same thing. We have very detailed asset models, and so the solver is able to do things like look at the effect of wind on poles and pole failure and cable failures and vegetation intrusion on the cables and the effect that it'll have on the power system, whether it's relay operation, reclosers, and so on. All of that is captured in these models, and it will simulate all of those things correctly. And as I said, there's physics-based models for the buildings, so we have very good load modeling capabilities. And then there are a lot of tools that allow us to do sort of aggregations of different behaviors, and as I said, a lot of geodata capabilities that are built into it. So there's a bunch of modules also that are available. Human behavior modules to do connection with other systems, which is how Helix works. Helix is the co-simulation environment, which DOE developed. It was developed at multiple labs. It's amazingly powerful. You can integrate just a remarkable number of things using Helix. PowerNet, which is an ARPA-E CEC project to demonstrate transactive energy. The reliability module just implements the IEEE 1366 metrics measurements. So when you run a simulation for a year, for example, it'll tell you SAIDI, SAIFI, CAIFI, all that stuff. The resilience module basically does things like pole failure analysis and the ability to study, for example, how distributed energy storage can help mitigate those kinds of situations. As I said, revenue and tariff analysis, transactive energy, and then the different ancillary modules to do model sanity checking and import and export of data and optimization. There are a lot of subcommands that are used to basically do all this manipulation for you, because this is, as you can imagine, the quantity of data here is astonishing. And so these tools allow you to move this kind of data in and out of the simulator relatively easily. I wouldn't say it's perfect, but you know, we get data from so many different sources, and it all has to be connected up to the simulator. These tools allow you to do all of that. So yeah, there are subcommands, and then there are tools for actually doing things like designing filters, creating a transfer function for a building based on AMI data, all sorts of weird, quirky stuff that you typically have to do to make this kind of a simulator actually work. The Python integration, I think, is the most powerful feature of this tool. You can basically hook up an event handler to just about everything in the simulator at the top level, at the module level, at the class level, at the object level, and you can then, with that event handler, access data from any other object. So you can do lots of crazy stuff that you wouldn't be able to do in reality, but that's the key. Because a lot of the time, when we're trying to think about what are good ideas and what might become interesting technology development, you want to think about, all right, well, what if I could? And you can't go and just use a simulator for today's system to do that, because it doesn't allow you to do these kinds of what-if studies. So the ability to do all these kinds of things is what allows us to explore these sort of weird what-if we could do this scenarios that become the basis of you know, the investment that DOE might make in a new kind of technology that does something we can't do today.
Could you give an example?
Yeah, so imagine, well, so a good example is in transactive energy, right? Today, devices can't submit bids into a market. That's just not something you can do. But imagine if you could. How would the market change? What would the behavior change be on the market if your PV panel could submit a bid into CalISOs, for example? I used to live in California until a few weeks ago, but, right? So you can implement that in the simulator. Of course, there's a lot of caveats, right? You have the sort of billiard ball and marbles problem, right? You've got big generators and little generators trying to interact. But conceptually, you can do this. You can do the same thing with loads. And so you can construct a model that allows you to study that kind of an idea and see if it makes sense even, right? And see if it trips you up in some way that you didn't anticipate. right? Because the simulator will do all of these things, you might discover a behavior that you never imagined. And a lot of these very complex system of systems exhibit emergent behavior. And so the ability to sort of explore and discover, you know, the inherent pros and cons of a weird idea is sort of how a lot of these things end up being reality. So that's why we allow you to do that. There's online documentation available. I'll talk about some of the pros and cons of the way the documentation exists today and where it might need to be done a little bit differently. I will say validation is a huge problem. When you have a simulator that lets you do things that you normally wouldn't be able to do, how do you know if it's right? Well, you don't, right? You have to just do it a lot. And then you look at it and you go, does that make sense? And so a lot of the test cases we have came out of studies that DOE did where we looked at a scenario and tried to determine whether what it was doing was even sensible. Does it, you know, and then that became a test case. And then what we do is as we modify the code or add improvements to the code, we try to detect whether that scenario is fundamentally changed in some way that doesn't make sense. So, yeah. Yeah, absolutely, we do that. And that's what you use a valid way of doing it, right? Or is it up to a point, yes. Because of emergent behavior, I'll use the sort of Karl Popper model of how do you know it's right? You don't. You just know when it's wrong, right? If you can't reproduce the past event correctly, okay, that's a problem. But just because it reproduces a past event doesn't mean that it's going to reproduce alternative scenarios correctly. And that's where it gets really tricky. But we have this large number of test cases that we use, and basically every time you make a change to the code, it runs them all, and if anything looks not right, it will flag it. And then you have to, you know, crack it open, look at it, and that's never fun. So the challenge that we have with validation is that in order to do a lot of these tests, we need things like access to NOAA databases, right? And so this external access thing is a headache. Just this afternoon, we had a code change, and what's it called? FTP mirrors at GNU.org, down. It was down for a couple of hours. So it said the test failed because it couldn't access the databases, right? But the test didn't fail, it was just, right? So this is typical of open source software. You have these enormous number of dependencies, and any failure anywhere in the entire system of software causes the whole thing to fail. And so that's a real headache. But it's the world that we live in open source, and you have to just learn to adapt and live with that. All right, I want to talk a little bit about the user interfaces. I'm not going to spend a lot of time on these, but I'm going to advocate for them. I think the work that these people have done is really amazing. And it serves different kinds of user communities in different ways and very well to each their own. The first is what I think is the simplest way of doing it is you can create a project on GitHub with a template and put your model into that GitHub project and it will run. That's all you have to do. You just have to create the GLM file that describes your model, use the workflow that's designed for this, and it will run your simulation for you, and it will produce the results in GitHub Actions, and you can download your results. And it is by far the simplest way of doing it. You don't have to install it on your system. You just need to have an account on GitHub, and that's it. And there are tutorials that walk you through the basics of how to do this, but it is very, very straightforward. I'm a big fan of it because I can get my students to do this in like 10 minutes. It's very straightforward. It gets complex when you start to build these large, very interdependent models and you have external data access, and GitHub will cut you off at an hour. So if your simulation takes more than an hour, which I don't have many that do, but then that won't work. But for the vast majority of people, this is perfectly sufficient. And it's pretty neat because GitHub gives you the maintenance and the revision tracking and team build, right? A whole team can work together to build a model. Super convenient. The next way is the other tool that we submitted to LF Energy, which is OpenFido. This is basically a workflow management tool. It allows you to take data from a lot of different sources and construct a workflow that's highly repeatable. The goal at CEC was to make sure that results were reproducible. Even in GitHub, right? There's no guarantee that when you run it twice, you're going to get the same answer for a lot of reasons, right? The container might change. There's all sorts of reasons why things might turn out different. The purpose of OpenFIDO was to let, for example, a regulator have access to a model constructed by a utility, and they could get the same answer and then start to maybe explore alternatives or try things or do sensitivity analysis in order to convince themselves that what they've been given is legit, right? And so CEC was very concerned about having a tool like that available to make sure that users of Arras Energy and other kinds of simulators would have the ability to create workflows that were highly repeatable, highly reproducible, and managed. The next one is something that you may not have heard of, but I think you will start hearing much more about. It's a tool called Marimo. Marimo is, you think of it as a Jupyter notebook that solves all the problems with Jupyter notebooks, right? I don't know how many of you have used a Jupyter notebook, right? Okay, what's the most annoying thing about Jupyter notebooks? Yeah, you change a cell and you don't know whether or not it changes everything else. And the only way to fix that is to rerun everything, right? Which can take a while. Marimo solves that problem. And it solves it in a beautiful way. It creates a dependency chain and it updates things appropriately. It doesn't update them if it doesn't need to. It's got UI elements built into it. You can do, so this is a simple Marimo notebook that just takes a GridLAB-D model and allows you to explore the model. And it's amazingly simple to do. I really encourage you to look at this. This is this is going to change how we do this kind of work, and I think Jupyter notebooks are going to end up being a thing of the past. I'm really impressed by the work that these guys have done. Sorry, you were going to ask a question.
Yeah, I was just making a comment. The most annoying thing for me with Jupyter notebooks for mixed content is licensing it.
Oh, I don't worry about that. We're in the open source world. I don't worry about it. Okay, and the last UI I want to talk about is Glow, which is Hitachi's UI. That's the one that was funded by the CEC. It's comprehensive. They basically created a UI that supports all the use cases that CEC wanted, and underneath is GridLAB-D or Arras Energy. I encourage you to look at that if you really need a full-blown user interface the way you might find with most other tools. They basically solved all of the problems that existed in the original GridLAB-D, which had no UI at all. It was all command line, and it was just difficult to use. And so they've got pre and post processing, a user community that's growing around the tool. It's got all the different elements of the UI you would expect to see. From model construction, drag and drop. I have my issues with drag and drop model construction. It allows you to not know what you're doing. That has some side effects, but it's got some very nice post-processing tools that are built in, and so I encourage you to look at that if you're interested in using the tool. All right, the last part of this I want to talk about is the issue of open source and how you deal with some of the problems that come up in open source when you're talking about a tool this complexity and potential impact. Is a utility going to adopt it as part of their mainline production? You have to deal with some of these issues before you can answer that question. So what I've found in talking to people about this is, first of all, people don't really know what open source means. They think open source means you don't have to pay for it. Yeah, no, you do. You just pay for it in a different way. You have to know how to use it. You have to know how to deploy it. You have to know how to maintain it. You have to be part of the community that maintains it. And that community building can be very difficult for open source software, and it is certainly for this project itself. The other thing that we've found is working with utilities, each utility has its own way, and I think Abdur can confirm some of what I'm saying here. It has its own use cases that it validates in its own way. And sometimes those validation processes aren't even known outside the utilities. So for someone to come in and try to sell, quote, sell a tool like this requires you to get through this process. And that process can take many, 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 many months to run through. And there's no guarantee you'll actually be successful because some of this is sort of institutional knowledge. It's not formally documented anywhere. It's people who've been doing this all for many, many years who know what needs to be done and how to do it, but they can't tell you, oh, here's this document, read it, this is how we validate every tool. No such document exists. And so that's very challenging, especially in larger utilities. The other problem that we run into is that code and data provenance is a real issue. And I'm going to talk about this a little bit more detail in a second. But I want to point out something that I think most of us don't realize, is that when we talk about data, licenses don't apply. Sorry?
Hang on.
Oh, yeah, you might have to hang on for dear life because, when you're talking about tools that need both code and data to function, the licenses don't cover the data. You have to deal with the data individually on a case-by-case basis. And Arras Energy is definitely a case in point. There's an enormous amount of data that comes with it that has to be open data, but it's not open source because there's really no such thing. And then the other issue we've run into is that utilities typically use what are called whitelists for access to data, they don't do it the other way around, right? Everything is forbidden unless expressly permitted, right? And so let me go through these a little bit in a little bit more detail. So when we originally got funding to do this work, our funding agencies thought open source meant freeware. We know that's not true. What open source means is you can see the source code and you can contribute to the source code, but it does not mean that you get to use it necessarily for free. And that was not well understood by most people. I'm not even sure at some point I understood that very well. I think it takes a while for people to come around on that one. Okay. The other thing is that there are lots of different open source licenses, and some of them are not very user-friendly, and some of them are not very developer-friendly. And the Venn diagram for these leaves only a few that are really compatible with what we're trying to do. And so that's an issue. And then I think most people don't know that government has rights that supersede the licenses, blanket. The government has incredible rights. And so most folks don't know that, especially the US government has walk-in rights. It can just come in and say, code's ours, and walk away with it and use it for whatever they want. Because at some point they invested in it, and that gives them these rights, and there's nothing anybody can do about it. So if they want to, yes, well, find me a piece of software that doesn't have something the US government didn't contribute to. When you look at the big dependency tree, yeah, I doubt that there's very many out there where that's the case. Very many large-scale ones like this, where that would be the case. And then I think the documentation that we've got isn't very well suited to some of the users that we have. It's well suited to developers, it's well suited to sort of modelers, but not to the general user. And I think that's going to be a limiting factor for a while until we figure out how to provide documentation that is better suited to the general kind of user. So I mentioned this community building problem. We introduce upgrades a lot. And the upgrades come from a lot of different places, and some of them don't get as well reviewed as they should. They're really interesting, but what the difficulty is that a change or feature that you introduce in one part can have repercussions elsewhere that no one thought of, and you won't even notice because the test cases don't check that sort of pairwise interaction. And when you've got thousands of different components that are interacting with each other, you can't exhaustively explore all those pairwise interactions. And so this is becoming a real issue for us as we introduce these kind of new features that people are looking for. This is, of course, also associated with what we call feature creep documentation, right? You get all these neat new features, but they're not documented always to the same degree as each other, and so it's not always easy to tell how one change is going to affect another. So we have all these processes in place, but they're not always sort of used uniformly well to manage this. We have a lot of issues with maintenance, and we struggle with the backwards compatibility problems, particularly with Python modules. It's a huge headache. You do a security upgrade to a Python module, and it comes with a deprecation, something that you use, and there's no substitute. There's no way around it, and now you're stuck between a rock and a hard place. You either do the security upgrade and you lose the feature, or you keep the feature and you have the security vulnerability. What do you do? And this is becoming a real headache because there's a lot of Python modules are rather sloppy about their compatibility, especially backwards compatibility. And without naming names, I'll name NumPy. It's just notorious for doing this.
Is this a symptom of a lack of software engineering professionalism?
No, I think the people who do the NumPy development are very good at what they do. I did think it's a symptom of not understanding your users, right? In the utility industry, when you put a piece of code out there, it needs to work for 30 years, not a year and a half to finish deprecating that particular function you don't want to maintain anymore. This isn't going to work long term. This is just not going to work. So we need to deal with this issue. I just don't know what the answer is right now. So, I think I've said enough about that.
So
Yeah.
What was mentioned this morning that you would more than start to look at contracts based on features? Was that naive slightly?
I don't know. Yeah, I think so. All right, so use cases, right? So one of the issues we deal with is that people come to us and say, wow, this is a really great general tool. Have you tried to do this with it? And we're like, well, I guess you could. And then when you get into the details of trying to do that, you realize, oh, well, okay, that's not as easy as we thought it would be. Yes, it was designed to allow you to do these things, but when you go to do it, the devil is in the details. What we discover is that there's a lot of local stuff that we just don't know about. And there's not a very systematic way of dealing with those kinds of issues, so you tend to get a lot of ad hoc solutions that don't generalize very well. And I think this goes to the larger problem that there isn't really a standard. I hate to use the word because I hate standards, especially before you know what you're doing. Standards are fine after you know what you're doing, but standards to drive what you're doing, nah. And I think this is an issue, right? We don't know how to define use cases in a way that allow us to engineer software in a systematic manner. It's still sort of a human-intensive, ad hoc process that makes it very difficult for us to design a change to the software along with the validation of that change and so on. This is all, it requires an immense amount of expertise that I think is sorely lacking in the community. And then, as I said, validation suffers from issues with access to data sets, and this is just, I think everybody knows about this problem. Code provenance, another huge issue. Modularity is the basis of open source, and we are never going to leave that behind. That is essential. The problem is that you end up with these very complex dependencies, and an update that's poorly implemented or thoughtlessly implemented in one can have huge ramifications throughout the system and basically cause complete failure of the entire system. And this makes maintenance of the code incredibly labor intensive, much more than it would need to be if people were more diligent about how they do these upgrades. And so this review process is just becoming incredibly burdensome. And I think this is going to become a focus of LF Energy, trying to figure out how to deal with this problem. As I said, data is now code, right? If you think about how Gen AI models work, torch is not the issue, right? Nobody's worried about that. It's the weights And the weights are what's actually now driving the behavior of the systems that are using the output of these Gen AI models. Nobody knows how to interpret these weights. Nobody knows how to even license these weights, right? These models, they're not treated as code. There's no legal framework even to think about how to do this. It's done on a sort of case-by-case basis, unlike what we have in code, where we have standard licenses that everybody knows and understands, and you know how to treat the code when you get it, and you know what you can do. So I think this is an emerging issue for us, and we are seeing it. We have, inside GridLAB-D, we have machine learning power flow solver enhancements, where it observes the Newton-Raphson, and it learns from the solution and then creates a faster version of that solution, which it uses. Well, right now, we don't tell you what the weights are. We could, but there's no mechanism to know what to do with those weights. Those weights are very particular to that solution. They actually might even reveal things about the network that you don't want revealed. This is tricky. The other thing I want to bring up is the XZ. I call it a near miss because it didn't actually happen, but it was so close. This is basically where somebody deliberately introduced a vulnerability to give themselves access to every Linux system in the world, backdoor access. That is scary. And that kind of thing, the fact that it happened in such a core component of the Linux system, should give every utility pause. You need to think, how are you going to make sure that this kind of thing doesn't give people access to your systems, and how are we going to be comfortable that those situations will be detected before they occur? You need to read about how the guy who found this detected it. And then you think about, that was an accident that he found it.
Is this the one that went into a release candidate that never made it into production?
Yeah, way too close, way too close. So I just suggest you read up about it. As I said, whitelisting is an issue. We use an enormous amount of URLs in the system. Depending on how utilities implement their firewalls, URLs whitelists are okay, but sometimes they use IP addresses for their firewalls, in which case URLs are not okay, because you go to, for example, AWS, you might get a different IP at different times for the same URL. So clearly that's not going to work. And so this is something that needs to be addressed, and we don't have a good system for addressing this. What we do in Arras Energy is we produce a list. It's like, I don't know, 60 or 70 URLs that are used to operate the simulator. And the poor IT guys at the utility have to whitelist all of those things, and that comes with implications, because some of these things that you're whitelisting are not .govs, they're .edus. You wonder about some of those. Very good reason to be concerned. So in summary, I just want to say, there are some really fantastic pros, but there are some cons about open source. It's certainly cost effective, especially if you're trying to get the latest and greatest. But because there are issues because of how easy it is to get things about whether you can get the support that you need. You have great flexibility and customization, but customization implies hidden costs. You have a great collaborative community that provides you with very innovative services and products built on the tools, but that usually results in fragmentation of knowledge and resources and potential issues with trying to find the right person to solve the right problem. There's some great transparency benefits. You know what the code is doing. You can read it. You can look at it. But sometimes that comes with compatibility issues and implications about whether or not the next version will be compatible with the system that you've got, or you've lost some of that compatibility that you needed. We often talk about security as a pro, and it certainly is. The fact that you can look at the code and you've got a very large community of experts who look at it and they can tell you, yeah, that's the right way of doing this, is a huge benefit. It also means that when you find a problem, if you don't fix it right away, and deploy that fix in a way that allows you to do the upgrade without losing some feature, then you've just told the whole world how to break into your system. So, you know, with the freedom that it offers comes the responsibility and duty to maintain it, and it's something that we struggle with in this software. It's got a lot of features that allow you to do things that are kind of scary. So it's a bit of a mixed blessing. So I think with that, I'm at time. I just want to give you access to, you know, the list. If you want this presentation, just take a picture of that QR code. I'm always available. Like I said, I just left the lab, so I'm now a consultant free man. After working in the National Lab System for 32 years, it's a strange feeling, but I'm going to enjoy it. So with that, if you guys want to hang out, we can talk. Free to ask questions. So.
I have a uber philosophical question. I did something. Okay, you said, yeah.
Well, I don't need it, so if you want.
I have an uber philosophical question. I wrote something a little similar to this actually in 2010, 60,000 lines of C++. And I wondered, you mentioned that it always converges. So I want to abstract away all the kind of just technical stuff going in the background. So your housing module is woomph, your load flow woomph, your decision making woomph, even your control systems, and reduce it down to a federated system of areas which have their own, I guess, autonomy, sovereignty, if you want. And you want to solve it. And I thought I would just throw it as a solver, and that didn't work. So I wrote some graph theory, and I went around each particular federated area in an order. If I could capacitate it, I did. If I could solve it, I did. And then I moved on to the next one. And I just, yeah, and I have no idea whether that solution is universally applicable.
Yeah, no, so you're absolutely right. So when I say it always converges, let me point out, it's the top level solver that always converges, right? So for example, if I didn't have top level, I had federated systems. Yeah, so that's a little different. I'm not sure what that would do, so I'd have to think about that one. So when the top level solver sees one of the lower level solvers not converge, it's usually because there's a problem. And so it deals with it in a different manner. So think about what it means when a power flow solver doesn't converge, right? That doesn't mean that there isn't a solution. It simply means that the eigenvalues don't give you a trajectory to the steady state solution, right? That doesn't mean there isn't one, right? So I think that's very important to understand. A lot of these solvers represent physical systems which do end up in some state. It's just that the numerical methodology can't tell you what that state is. So what the top level solver does is it has a fail-safe. When a lower level solver fails to converge, it has a way of saying, all right, and then that must represent a condition of some sort. So for example, if a power flow solver doesn't converge, there's an assumption that it represents an infeasible numerical state, which corresponds to some exotic physical state. And then it just uses that. So there are tricks involved. Now in buildings, for example, buildings are physical things. If you take for example, the dynamic model of a building and you solve the equations, you see that it's, what's the word I'm looking for right now? That it's over damped, right? So it always has a solution, right? The roots are positive, right? So and so it always has a solution, and you can always calculate it. It may not be easy to calculate it, right? It might actually have a sufficient mass that it does something peculiar, and then the solution becomes tricky to get numerically, but it exists. In controls, you might find situations where it can't tell you what's going to happen, either because it's an unstable control, but then it's a control design error. You need to fix the control system, so that's fine, right? It's just not, it's not gonna work in reality, so it certainly isn't gonna work in the simulator. Or it might not be a causal system, right? Which case, what happens is that you get two things changing states dependent each on the other without getting the ordering correct. And if you have a non-causal system, well, again, you shouldn't be implementing that. That's not real, right? You can't do that in reality. You have to put a delay, and as soon as you put the delay, the problem is solved, right? So it will catch anything that is not real, and it will do something weird, and then you need to fix it.
When you go to optimal solutions, you can't actually determine whether the solution, you can determine it's optimal, but you can't determine it's unique. Is that an issue for you?
All right, so.
Okay, I've got really good.
No, so I will tell you, the optimization module, it requires that it be convex. Problem solved.
Okay.
Which means you need to be good at your relaxations. If you're not good at your relaxations, you're not going to make a good convex solution to your non-convex problem, and it'll just give you weird stuff. But you know, you go in, you use CVX, and it'll tell. First of all, you construct your problem, you feed it into CVX, and it'll tell you whether it's disciplined, et cetera. It tells you everything you need to know about whether your problem is even okay to use. But it requires that it be convex, because if you think about, you're trying to solve, let's say, a whole year of solutions, and you're, busy trying to optimize the settings on a load tap changer. You can't afford the time required to, do a global optimization on a non-convex problem. It has to be convex in order to make it find the answer like that. So, you win some, you lose some, right?
No, I don't need it. Much less technical question, but you want to grow a community, you were saying, that's one of your goals. What is currently blocking you doing that? What is in the way? Is it knowledge? Is it technical?
If I had the answer to that question, I think I wouldn't have that problem. I don't know exactly, and I thought part of what I think I need to spend more time doing is better outreach, to try to get a better understanding of why that community is not forming around a tool like this. I think part of it is the complexity. I mean, so 500,000 lines of code just for the solver sets. No one wants to crack that thing open. It's misery when you go in there, because it's developed by a large number of people over a period of almost 20 years. This is not code that is friendly to building a community. So something needs to change, and I'm just not sure what it is. Yeah?
Helix has this very interesting feature where a packet drop, and I think even latency can be added to the data exchange between networks.
Yeah.
Are the hooks there in Arras to be able to implement this?
Only through Python right now. The connection module is the module that does Helix's connectivity. And I think it's part of that module, but as far as between other modules, because you can look at another object's data sort of while iterating, there is no built-in delay unless you create that. There's a filter object that implements essentially a transfer function, a z-transform, right? And so you can build in delays using the filter, and you can distort the data using the filters simultaneously. You can do both. So there are ways of doing it, but you pay a bit of a performance penalty, because you start throwing filters all over the place. You've got to update those, and it gets stuck in the innermost loop, which is really not the best place to be putting such a thing. But you could do it in Python. You could just create an object that does the communications in the way that you're doing it, that's not supported by the connection module, and it'll work. All right. Time to party.